Good day. My name is Tione Grant, and I'm an applied math chemical engineering major and a recent transfer to the University of South Florida. Today, I will be talking about the research that I conducted with Dr. Greg Winnell this summer entitled Is Lindbergh Bay Eroding Since the Airport Expansion on St. Thomas? To give you some insight into where the focus of my project, Lindbergh Bay was originally referred to as Mosquito Bay before the airport construction in the 1920s. In 1992, there was a desire to expand the airstrip, and the bay sediment was used in this construction, leaving a significant hole that remains up to this day. Many residents have maintained the idea that since the dredging of Lindbergh Bay, there has been an increase in beach erosion. So the focus of my project is indeed to see whether this is true. So the project's goal is to use wave propagation analysis across the Lindbergh Bay hole area to determine whether the present hole is indeed a factor in possible erosion on the beachfront. To give you some information on waves, waves are a medium of energy transport that is created when a disturbance in the water lifts it above the water's equilibrium line. Gravity would then push back, creating a spring action. And waves are essential when it comes to the geography of beach areas as they move sediment on and off the beach shore. For this project, our methodologies focus on modeling the Lindbergh Bay area in a one dimension and then developing a script to model wave evolution and erosion, the wave evolution and erosion equations. Down there we have the wave evolution on the left and the sand erosion potential equation on the right. When it comes to the wave evolution equation, we negated the effects of bottom friction and wave dissipation, seeing that entailed some other information that was not necessary for this project. So for this project, our equation was the wave generation due to wind minus wave breaking. In terms of the sand erosion potential, it is a ratio of the sand that is removed from the beach compared to the sand that is put back on the beach due to the movement of waves. When we look at our results, I want to focus on the bottom graph and then move to the top. So for the bottom graph, this is a one-dimensional interpretation of the Lindbergh Bay area. So we see that in blue, this is the hole that is present, and in orange, we see that there is, due to data interpolation on MATLAB, we're able to, in a sense, fill the hole and to model the wave over a supposable filled hole. Now, in the top graph, we see that as the waves travel from the depth and come closer and closer to shore, we see that there is no change in the wave height. As we enter the hole now, there is a drop in the wave's height as they enter the hole, and then there's a significant increase right as the wave leaves the hole. Now, when we look at the wave, the hole being filled and wave passing over that fill, there is no significance. There's no rise in the wave height. There's just dissipation as the wave comes to shore. Now, this rise in wave height is due to the wave crashing onto the shore. And due to this breaking, that is what causes the erosion that we see on the beach each and every day. The increase in the wave height and thus the dissipation of energy that would indeed occur. So looking at this graph, we focus on wave power compared to the erosion potential. In the beginning, as wave power is quite low, there is no significant difference in the erosion potential. However, as the wave power increases, we see that there is a large difference between the erosion potential with the hole being present compared to the erosion potential for the hole being filled. And one example where this is very important is during our hurricane seasons, where the wave power is far greater than it would be during our regular seasons or dry and wet seasons. So thus, looking at this graph, it's clear to see that filling the hole would indeed be the best option. So, conclusion to the project: smaller waves have similar erosion potential over both seafloor interpretations. The wave breaking height of larger waves would increase with the hole being present compared to the hole being filled. And as wave power increases, the erosion potential is significantly higher with the hole present, especially when it comes to powerful waves that we will see usually during hurricane season. For future work, we wish to look at our project from a two-dimensional standpoint, and in order to do so, we would like to implement the use of the SWAN data modeling. Then we want to compare erosion with the increasing water levels that we see due to climate change, and whether there's a there's a greater significance in the erosion potential as the water level increases, or whether it stays the same even with that water level rising. Thank you for listening. These are my acknowledgements. I want to thank my mentor for the work he has put in to help me. Thank you and have a great day.